homemade sub, I think, right, in a lake in New Hampshire by all accounts. And so the relevance of this, of course, is that we've talked about forces on structures so far, and so other forces on structures would be what give us buoyancy, right? There's a mismatch underwater in the pressure that's acting on the top, larger pressure on the bottom, no weight to hold them apart, so it rises. So it's really just a force on a plane type problem that we'll talk about today as we continue from our stuff. So that's one thing. I guess I wish I knew if I could move between YouTube screens with a shortcut. I don't want to do that. This is kind of interesting as well. Same deal, but on a different scale, I suppose. I guess an emergency breaching of a submarine. I guess you probably want to make sure there's no one above you before you do that. And the chances of having someone above you, I guess, in the middle of the Pacific Ocean are probably quite small, but not zero. And so the other item here is the Ehime Maru disaster. And that was exactly the case where that wasn't the case, that a submarine did an emergency breach because they had some visitors on board, dignitaries on board. I'm sure legislators, to be able to persuade them that investing in the Navy is a good idea. And it came up underneath a Japanese training fishing vessel. So high school age students learning to be fishermen. Aquaculture is a big thing in Japan. Seafood is a huge part of their diet. Some of it is, of course, raised in farm settings offshore, but other stuff is deep sea fishing. So this is probably what this is. And so the Greenville came up underneath this and sank it. Yeah, so unfortunate incident, and maybe a number of people died. This is not a movie. I don't know, when was this? Does it say a date on it? This must be in your lifetime, 2014, so 10 years ago. Still quite young. So the Costa Concordia was again, buoyancy, was a cruise ship that the captain wanted to impress his passengers by doing, or perhaps people on land, by doing a sail-by close to land, and didn't judge it quite as well as he should, was he, and clipped the shelf on an island, ripped a piece out of the boat, and the result is the left-hand video here. And so I think maybe 40 people died in this. It was just a cruise ship. September 2013. Salvage operation, $1.2 billion. 32 people died. But again, this is related to buoyancy. Quite clever, actually, the salvaging operation. So it's sitting on its side. You put some tanks on the top of it. You fill these tanks with water. They have some dead weight. And you yank it over with some kind of pulley system as well to get it upright. Once it's upright, those tanks are filled with water, so it's really just rotated onto this pedestal, I suppose, that you've created underneath it. And then you evacuate, pump out the water from the containers. I guess you move one down, so it's obviously, if it's empty, it has no use as buoyancy unless it's in the water. And so you rearrange the containers, you pump water out of it, and you sail happily off to do whatever you need to do. So buoyancy, that's quite an interesting operation. So not a good problem to have in the first place, but an interesting solution to it. There must be a hurricane somewhere, I'm not sure. And I guess also salvage. The Glomar Explorer was a ship that was made after a Russian sub went down in the middle of the Pacific, and the Allies, the US mainly, wanted to get hold of the whatever technology and codes might be on board. The Russians didn't know where it was, their own boat. And so there's this plan to build a boat that was for deep sea mining, the Glomar Explorer, financed by the CIA, that went to all the trade shows to get investors to understand that they're going to go deep sea mining for nuggets, nodules, manganese nodules on the seabed. But actually their whole thing was to build this boat that had a keel that opened up, so it was you could go into the water directly. Had these big masts to be able to actually lift the boat off the bottom of the ocean. I don't know what depth it is. Does it say? It was run by Howard Hughes. He was the guy who fronted it. I don't know. Soviet diesel-electric submarine K-129 sank in the Pacific Ocean, 1,500 miles northwest of Hawaii. And so they lifted it, and it broke in part, and part of it remained in the clutches of what was bringing it up, and the other part drifted back to the ocean, and they brought it back and did whatever they did with it. So, again, I guess buoyancy only in that the ship is open. I guess you can open the bottom of a ship if you have enough buoyancy around it to do that, just like a catamaran, right? Catamaran is on the floats, and there's a gap in between the floats on either side. So I think that's it. And of course the Kursk. Fine. And the Kursk was another submarine disaster in the Soviet Union that almost cost Putin his job, I guess, around the time that probably you were born. Is it 2020? Is it 2000? Does it say? Yeah, 2000, August 2000. So anyway, some stuff. Right. So today, okay, let's get going. So any questions before we get rolling? Maybe today we'll talk about summarize our stuff of forces on planes. We'll talk about forces on curved surfaces. We'll talk about buoyancy, as you could imagine, and maybe leave 5 minutes to talk about the test week coming up just at 8:45 as we get going. So that's probably what we might do today. Okay, any questions before we get going? Okay. What am I looking at? What's that? Doesn't sound... Yeah, fine. Wrong note. All right. So, last time, why don't I do this? It's useful to recap. Maybe I can do this. And I don't want to draw this again. You already have this diagram, but we can talk about it. So I want to do this. I'm getting pretty skillful, don't you think? All right. Why don't I talk about it in terms of the last thing we actually talked about? So the last example we did, let's just do it from a perspective of what we did. Remember the gate that was hinged at the top, that was vertical, that had a bottom part, if I draw it to perspective, that looked like this. So big picture for this is to, I want to do this. And what else? Right. So if we look at these individual components, this is the centroid of each of these plates. That is where we use to calculate HC. If it's aligned vertically, then this is YC, because it's in the Y direction. It happens also, if it's vertical, that it's going to be HC as well, right? Because it's vertical. If it's not, if it's inclined, then YC is not equal to HC, but it is in this particular case. So that's where we calculate the magnitude of the force, and we use this centroid height here. This is always true. And this is just an extension of what we talked about in the first couple of weeks, which is that the force on a horizontal plane is equal to the pressure multiplied by the area. So we know this. I mention that because it might be useful on next week Friday, a week today. We talked about this in the first week. And so this is just a reflection of this. This is the average pressure in the first term times the area. And we get that from the height. In this particular case here, this would be if this is 1, 1, and this is 2 for plate 2. This is the height to that, so we can calculate the pressures acting on those. And so we have that from this expression here, as you know. But, as we know, it doesn't act through that location. So we have to calculate the center of pressure. The center of pressure is given by YR, which is equal to, I guess that. This we can call delta Y, and this whole thing, even though I'm running out of space, is these two things added together. This is YR. And so the location where the force acts horizontally is F1 acts at this point here. Always symmetrically in the middle of the plane, just because you can imagine that there's equal forces acting on either side to try and swivel it. So it's down the center line of this. And this magnitude of location is given by calculating this, which we can also write, if you like, as YR is equal to it's already written. I was going to write it in two parts. YR is equal to YC plus delta Y, right? These terms here. Other way around, I suppose. It will always be below the centroid. This is called the center of pressure, and it's the point where it acts. And we can always calculate it from this expression. If we calculate the magnitude of the force acting vertically at this point, we get force 2 from the location of HC, which is this. And its point of action will be, as we explained last time, if the Y goes off horizontally to infinity, then on a horizontal surface, actually as we just said in the first expression, whether you have a liquid or a gas acting on this horizontal plate, the pressure, the force is always equal to the pressure times the area. And for a horizontal plate, the location of action will always actually be the centroid. So the expression above is what you might need next Friday. It's on the sheet already. You don't need the point of action. We said that it only covers weeks 1 and 2. But we did use force is equal to pressure times area within those weeks. And so that's all we need to know. And I guess the final thing, so we talked about needing 3 things. 1 is you need to calculate the magnitude of the force. 2, the location of the center of pressure, which is the point where it works, acts, which is given by this. And I guess the 3rd was a failure mode, if you like, right? And in that example, what we did, the failure mode was drawing a pivot that was here. And from that pivot point, we could do, quite simply, F1, L1. F2, L2. They both act counterclockwise. So to keep it closed, we need to apply a moment. And so the moment we need to apply, actually I guess in the question, the moment was applied by having a force in the other direction. It was called P, and it was by LP. I think actually that was the terminology we needed. So important for this third part is you have to prescribe a mechanism by which it fails. And so P times LP has to be equal to F1 times L1 plus F2 times L2. That's the essence of what we're trying to do. So that's in a nutshell what we're trying to do. I always worry about whether I should do what I'm going to do now as to whether it confuse you. So if this makes your head explode, then don't worry about it. But to misuse the expression, there's more than one way to skin a cat, wherever that comes from, I'm never quite sure, is that we could solve that problem in a variety of different ways. And actually some people came up to me last time, the y sub r thing from the second moment of inertia, and also decomposing the distribution into a triangle and a prism, they both give the same results. They have to, right? The physical system is the same. We're just solving it a different way. So you could solve this problem the way we just solved it now. You could solve it by having a bucket of water here onto which the fluid above it is acting, and the free body diagram is just this square here. It includes the water, it includes the pressure acting on this side, and it also includes the pressure acting down. There's nothing acting on the other side because this is air. Right? And we could also do it by doing it this way. It's a bit confusing. The free body diagram has to actually do this. Has to go through the hinge to allow this block of water to rotate. Can't go outside the wall on the upper part. Has to go inside. And so if that's the case, then what happens is that on this upper part here, there's a pressure distribution acting inside this wall in this direction, and it exactly counters this pressure distribution acting here. And so once you cancel this out with this, you end up with the same as this. So these two are the most usual to try and use. But if you went through these and tried solving the problem, you'd end up with exactly the same solution to it. It's just a different way of being able to divide it up, divide and conquer. Right? So free body diagrams are our solution. Perhaps you thought that after statics you'd never use them again, but certainly in what we do in this class, it's kind of throughout what we attempt to do. Okay? Okay? So don't get hung up on that. It's just an aside, but only to make the point there are multiple ways to solve these problems. Okay? So these are the fundamental equations that we need. We'll talk a bit about curved surfaces, but and then after that we'll talk about buoyancy. These are super contrived problems. This is a stupid problem, but let's just quickly look at what it would be. Why would we want to divide a drainage conduit into half and look at the forces? Well, we might want to do it just because we can. So here's a static fluid in a circular section. I guess before we do that, I didn't mention, these are standard results. This is the second moment of area around the centroid, and they happen to conform to standard results, which you have in your book. If they're on a test, not on this test, but if they're on a test in the future, you'll have seen that these turn up in the question. So for a circle, it's a standard result. For a plate, which is a much more usual one, we've used this already, it's a standard result. The centroid is always located directly in the middle. The centroid is directly in the middle. The centroid is a third up from a triangular distribution, from what we talked about before. It's a third up from every side, actually, as you know. And it's 4r over 3 pi up for a circle. So this is the point which would be the center of mass. So if you have a circular disc and you're balancing it on your finger, the point that you'd balance it on would be this point here, the centroid in each case. And this would conform exactly to this gray-lined point in the middle of our plate, gray-lined point. That's the center which the plate balances around. The point where the pressure distribution balances around, if you put it on my finger, is actually this other point. So but perhaps that's confusing to talk about it. Egghead professor stuff. So these are standard results. So these are the terms that we typically use, we've used already, and that are in your book, and that we may wish to use in the future. Actually, we need to use this one now, right? So we know that this is equal to actually, we don't need this, we need this one. So the balance point of this distribution is 4r over 3 pi in from the sides and the top, and we'll need that to be able to solve this next problem. All right, so if we're stupid enough to want to do this, we want to calculate what the resultant force is that acts through this system. How do we do that? Well, we make a free body diagram, we cut it off. If we cut it off, then the pressure distribution on this side will look like this. And the magnitude of this will be given by this point here. The pressure distribution on the top is 0 pressure, so there is no pressure acting downwards. So this is 0. And so for free body diagram, there'll be two forces. F1 acting horizontally, which is the resultant of this, and the center of gravity acting vertically. So we calculate each of those. Horizontal force is equal to the unit weight times the area on which it acts times the centroid. This is what that looks like. I'll use gray again to draw the locations. So this is HC. So HC is equal to 1.5 feet. Unit weight of water, never like these English units, 62.4 pounds per cubic foot. And the area, I think, is a 1 foot length. 1 foot length. So the area here is 1 foot by 3 feet, which is this. Multiply those out, you end up with pounds. The weight acting downwards is the unit weight. So this unit weight, as you know, is rho g. The area of a quarter circle is pi r squared divided by 4 times 1 meter. So I guess this is area times 1 meter into the page. I guess not 1 meter, 1 foot, I guess. And that equals whatever this is, 440 pounds, which is FV. If we want to then take those magnitudes, we have FH, and we have FV, which is W. I guess if we had a superposed pressure on the top, which we don't, then we'd have something else. And so we know from those that we can use Pythagoras just to calculate the resultant of those two vectors, which is this, and we get FR. And if we wanted to, from those, we would be able to calculate exactly what this angle is, just from sines and cosines, because we know this length and we know this length, and we can calculate this, and so the direction in which it acts is this. And if you wanted to, you could take these two forces and take moments around this central point, and you'd find out they exactly balance. So the resultant actually goes through this central point. I don't think that's an important thing for us to do here, but it's just... and the rationalization of why that happens is that we know that pressures act normal to this surface. And so all those pressures physically act by definition, right, through this point here. So it acts at an angle which is defined by this, and we can calculate it using this expression here, just from these different lengths, and pull it out. So we know in this case that it acts through here, and we know that it acts at some angle where this is the angle that we've just calculated here. Okay? If we want to do something fancier, I don't know whether I want to do this either. All we would do, actually it's just the same as the example we did before. Here we decided that we could solve this problem. Yeah, actually it's this, right? We said that we could solve this problem by doing this, by looking at weights that are acting, and this weight has a pressure that's acting on top of it. We could solve this one with a curved surface, where instead of this right-angled gate, we have a curved surface. We have to calculate the weight of the fluid according to the cross-sectional area of the quarter circle. We have a pressure acting above it, which we can calculate what that vertical force is, because this is just going to be equal to the height of the centroid, which would be this depth here, times the unit weight, times the area on looking downwards in plan view. And we could use that to solve this problem. So I'm not going to do that. So the relevance of this is that so-called tainter gates are structures that control water behind impoundments, sometimes in dams, sometimes this was at Bay of Fundy in Nova Scotia, as it turned out, many, many years ago, hence a black photocopy. But this is the gate, a very flimsy structure. You can see that these stanchions go to a hinge point somewhere in the future. It's got a very light covering, and this sluice just goes down to close off the flow. And because when you have the pressure acting on the back of this gate, acting normally to this, it can be a very flimsy structure, and it works around a pivot point, but this can be a very light structure to be able to do that. And it can be a light structure including this because there's no net moment on this, because if everything is acting through this fulcrum, there is no moment that's applied on this. So you don't have to fight against it to raise it. You can raise it quite easily, raise it and lower it quite easily. Don't want to talk about that. These are too dangerous. Okay. Let's not solve this, but let's think about a thought exercise. So there's always a wrinkle in these somewhere, and you have to see the wrinkle. The wrinkle in this is that you have a cylinder. It's sitting in oil. Pretty big cylinder to be sitting in oil, kind of, but anyway. So these are egghead book questions. You have to calculate determine the horizontal force the cylinder exerts on the wall. And so there is going to be a force here. I can see from below it's called FA. There's going to be a force on the other side. What you could do is easily just do this, as they've done below. And if you do that, then we can isolate this in terms of our free bodies. Don't care about vertical in this particular case. It's a horizontal force, so vertical forces are orthogonal, so they have no influence on the forces. This is the force exerted by the wall in pushing this back. And so you can imagine that there's a bigger force on the left because we have a big force diagram. So what's the force on the right-hand side? Is it this? No. Or is it getting fancy here, right? Or is it this? So if this and this are the same, then this would be the pressure distribution we have. Right? So it would be enticing at first thought to look at this pressure here, that, well, it's atmospheric above here, so it has to be atmospheric at this point here. But of course what we do know is that if you go from this location here to this location here, they're exactly the same elevation. And we know that this expression says that, just like the manometer equations, any location at the same elevation has to be the same pressure in a static fluid. And we can get from this location one to the other in this. So the bottom line is that the magnitude of this pressure has here, of this diagram, has to be the same as this magnitude here. And so we can calculate exactly what those would be, and that's what's done. And so actually, I suppose you can solve it in a variety of different ways, but one straightforward way to solve it would be to think of this force as being acting on a plate like this, right, where I do this. So you have HC and you have YR defined. And the other one would be a plate, which I'm running out of space for, but would look, and I'm not sure whether I can do the drawing justice. The plate would look, the vertical axis would look like this. Y equals 0. And the plate would look like, can you see my, this. And so again, this would be below the surface. And so what would the magnitudes be on this? The dimensions are what? So this is 3 feet, so this is 3 feet, and this is 3 feet, and etc. So this would be, if I put this on, this would be y equals 3. This would be y equals 6. I don't know where this has gone. Where's my colors gone? Oh no. And so, and this would be 4.5. Right? So the resultant force would be equal to unit weight of water times the area times HC, and HC is 4.5. Right? This would give you the correct magnitude, and what would A be? A would be 6 minus 3 feet, which is this height here, multiplied by the width into the page, 9 feet long. Okay. Make sense? Yeah. So just have to figure out how to be able to dissect these problems. So you could see that. Too much information, again, showing that everything, you can solve problems in lots of different ways. Too complicated for what we want to do here. Okay. So, there are lots of different ways to solve it. So the only way you get a lead on this, I guess, is practicing it. So you'll practice it in homework, so that's fine. You'll get some chances to practice this. Okay? The last thing to deal with then in this, I don't know why this has gone, oh yeah, fine, it's back, is to talk about buoyancy. And so if you came in late, well, why don't we go back? We have a bit of time. Where was it? Utube. So how does a submarine work? You know, obviously know how a submarine works. You go down, you take on water as ballast. You sink as a result of that ballast. You have it in your tanks. You have compressed air or some ability to store air, and you use that air to evacuate the ballast. And the submarine is now less heavy, and therefore is able to float by its buoyant weight, because all the people living inside are living in an environment which is at atmospheric pressure. And so we won't talk about that anymore. And so that's exactly how submarines work. And so how does buoyancy work? And so you might know Archimedes' principle, that the buoyant force is equal to unit weight times its volume. And so it's quite easy to show that. The easiest way to show that is by just doing this. We know that if we are working again in our XY coordinate system, then we know that pressures change as a function of P P equals P0 plus gamma y in this particular case, if this is y and this is pressure. And so if we do it differently, if we have pressures at two different heights, we have exactly this. P1, Y1, Y2. P1, P2. And we can think about do a circle. I like buckets. We have a bucket of fluid which has some weight W, has some cross-sectional area A. We have pressure acting on this, which is P1. We know that F1 equals P1 times A from what we talked about. We have a pressure acting upwards, which is larger, which is P2. And F2 is equal to P2 times same A. And we know from what we understand about statics is that F1 plus W is equal to F2. So F2 minus F1 has to be equal to W. And I guess we know, we could think about this. This weight is why these pressures are able to be different. It's the same as we talked about stacking buckets to get to the height of Everest. You take fluid in a bucket, you calculate what the weight of the bucket is, and that force is what's holding it up. If you divide that force by the area, that's the pressure underneath it. If you add another bucket on top and another bucket on top, then this is exactly what you get. And so if you take this away, this weight away, if you can magically ring it in a weightless membrane and take this water away, then all of a sudden it's not going to be in balance anymore. And so we could, I suppose, write this out as equal to P2 minus P1 times A. And we know that this is also P1 is equal to gamma Y1. So this is also gamma Y2 minus Y1 times A, which is W. And this is also equal to the unit weight times height times area. Should I use height? Perhaps I shouldn't. Let's use L. Right. If you subtract Y2 from Y1, Y is bigger, so this is L times A, and this is just equal to unit weight times volume. So this is the force that's keeping it in place. So this is just a static fluid that's fluid all through it. So we encase this volume with a membrane, and miraculously we take the water out of it without the membrane, flexible membrane collapsing. And then it's going to be out of equilibrium. The magnitude it's going to be out of equilibrium is equal to the buoyant force. So W is holding it down. You take W out, it's no longer there. The net force acting upwards on it is going to be the buoyant force. Buoyant force always acts upwards. Always acts upwards against gravity, I guess, officially, if you want to be pedantic about it. But for us, that's upwards. And so that's exactly what this expression is here. And so if you know what the volume is of the submarine, if you know what the unit weight of the fluid is that's surrounding it, not the unit weight of the fluid that's in the submarine, but the water that's around it, then you know what the buoyant force is. And so if you take on weight in the submarine, then that would act against the buoyant force to keep the submarine down. So that's it. Simple. Pretty straightforward. Well, I think I've seen it a few times, so it's straightforward to me, it seems. This same analysis, blah, blah, blah. And so, I don't know, let's do, as an example, let's do a quick example and then talk about stability. So the quick example is this. From the book, which hopefully you have, maybe you haven't, some may have had it. So you have a buoy, I call it a buoy, and it has some weight to it. So if you took the buoy and carried it on shore, this big orange thing you're staggering around with that has some weight to it that you have to hold. And so that's this W here. And you put it underwater, you tether it with a cable, and you want to calculate what the force is that you have to tether it with to be able to hold it in place below the surface. And so it's just a force balance, right? Forces acting downwards are the tension in the cable and the weight of the fluid. Forces acting upwards are the buoyant force. The weight we have, the buoyant force is equal to the volume of the buoy multiplied by the unit weight of water. And what we'd like to solve for is this. So we just rearrange it. Unit weight of water times the volume is seawater, I guess in this case. Fresh water would be 9.81. Seawater, I think it's given in the question. Or perhaps not. Seafloor, yeah, fine. That's a minor wrinkle. So 9.81 or 10.1. This is the volume of a sphere of radius 0.75 meters. And this is the weight that you're given, which is the weight of the big boy. Not in terms of kilograms, but in terms of adding apples to apples. So everything is in newtons or kilonewtons, and you have to add them together, and you come up with this magnitude. It's worthwhile noting that, again, the little wrinkles on these questions, if this was our cylinder, didn't draw that very well, but you get the idea. If this is our cylinder, then the buoyant force is equal to what we said, the unit weight of water, or the fluid, multiplied by the volume. And so in the way that we derived this, if we go back here, if the pressure acting on that top surface, how far did we go back? Jeez. If the pressure acting on this surface relative to this magnitude here, the differences in these two pressures, is constant for a given height. So if you move this down, so maybe until it was at this depth here, the top, then the bottom would be at this depth here, then we'd know that the change in pressure between, this is still what we've called L, so I've just shifted it down, and now this magnitude of delta P is the same, right? This is delta P, this is delta P. This is the difference between the pressure on the top and the bottom. As we've translated it down, the height of the buoy hasn't changed, and so you'd expect that if you moved this buoy down, then it would still be the same buoyant force. That's why the buoyant force doesn't change. It doesn't change as you go down in depth. So in other words, if I was too clever for my own good, and I took this and moved it down here, the buoyant force doesn't change, because it has the same differential in pressure acting up. And the best way to think about it is that you're removing water from this, and really it's that volume of water, that mass of water, which is providing the weight in newtons that's holding this thing down. And so if you remove that mass of water, then that's the equivalent buoyant force that's rising. Okay. 10 minutes ago, so there's an interesting problem here. You'd see it, I'm not going to solve it today, but you'd see it in other previous lectures. Exactly that. So what happens if you have a fancy system where you have a cover covering a hole in a container. The container has water in it. That cover is held down by a weight. So the free body diagram looks like this. The basic question is, what pressure do I have to apply in here before I break this cover off? So again, the pressure acting on the bottom of this, the force acting upwards, again, is equal to the pressure multiplied by the area. This is the vertical force that's acting, right, on a horizontal plane. In this case, it's a gas, so there's no density change, but that would also be the case if it was a liquid. And so the question is, what happens when you increase the pressure on this top force? So from what we've just said, if you look at the pressure that would be acting on this water, if the pressure was 0, then the distribution of pressure would look like this, and the change in pressure between the bottom and the top would be this amount. This is delta P. If you now add this pressure on the top, you might expect that perhaps there's a bigger force on this, but of course there isn't, right? You change the pressure at the top, the distribution diagram changes parallel. You move to this point here, and you move to this point here, and this delta P is exactly the same. And so you can surmise that the buoyant force that's applied here is always unit weight times the volume. Unit weight of the fluid times the volume. And this is the argument, right? No matter what the pressure acting down on it, the buoyant force is always unit weight of the surrounding fluid times this. In this particular case, the block has a weight to it, just like the buoy did. This would be a solid weight because it's solid. And so you can do a free body diagram just to write that you want to get P times A plus FB is equal to W. You know what W is because you're given it. You know what the buoyant force is because you know this is equal to unit weight times the volume, unit weight of the surrounding fluid times its volume, and you know the area of this plate, and so the only thing you need to solve for is the pressure. And then when you want to solve for the pressure, it just makes it difficult for you because it wants you to just solve the manometer equation, but that's it. But that's basically it. So that's buoyancy, and so pretty straightforward. Well, I shouldn't be so condescending to say that. It's not. If it's first time you're seeing it, then it's perhaps not so straightforward. But you can always calculate these things. It's really getting the recipe. So one thing is to understand the expressions, but the other thing is to be able to apply them. So that's buoyancy. Buoyancy is always given by the unit weight times the volume that's displaced of the fluid that surrounds an object. Whether it's an empty object with air inside or a solid object with solid inside, they both apply. The other interesting thing I think in talking about buoyancy is stability. And so we all know that if you have a sailboat, you put a lead keel in it so that it stands upright when the wind's blowing, and that is a problem in stability. And so we can look at how stable objects would be that are buoyant. The first ones we can look at are the simplest ones, which are fully submerged, like a submarine. And that would be that the center of gravity, so in other words, if this was a submarine and we had water, or we had lead in the bottom of the submarine, then the center of gravity of the submarine would be displaced downwards below its midpoint. The center of buoyancy, where the buoyant force acts, is always the centroid of the volume. So the analogy with our, bless you.
Thank you.
the analogy with our if we had a prismatic submarine, this would be what we've called in the past our centroid. So the place where the center of buoyancy would act would be right in the middle here. This would be C. Let's write it for Center County, C-N-T-R-E. So acts as the centroid. And so that doesn't change. That's controlled by the shape of the submarine and the water it's displaced around it. But if we use something as ballast, we can move the center of gravity, which if it was just a plate, if the submarine was just made of styrofoam and was homogeneous, the center of gravity would be right at the centroid. If we put more mass in the bottom, then it would progressively move downwards because the mass would be here. The balance point for this sheet of paper would be closer to it if I was putting it on a seesaw. And so that's important because if we give it a small twist, then the buoyant force acting upwards and the center of gravity acting downwards, these points haven't moved, they will tend to right it. The couple that is twisting this restores it to the vertical. That's why a sailboat works. If it's the opposite, if we have a keel in the top of if we're really not very smart naval engineers, and we put lead in the top of our submarine, should be just the same. Buoyancy works. Not so. You twist it slightly to the side, then the couple here, the couple as in a moment between two places, that's what the couple is, two forces acting against each other, tends to disturb it, and it would turn upside down until this was on the bottom, right? That's not really probably what you want, unless you want to be upside down sailing in your submarine. So we need to know that the buoyant force always acts at the centroid of the volume, cross-sectional area in this particular case, and the center of gravity is the balance point if we took a section and tried to look at it on a seesaw. That's the easier one. The more difficult one is when you have a free surface, because the center of buoyancy depends on the submerged profile. So the submerged profile for the center of buoyancy in this case is this, and in this case is this. So clearly, if this is changing as it rotates, then the center of gravity isn't going to change for this figure, but the center of buoyancy is going to change because it's the balance point of this gray cross-sectional area. So again, the same principles apply. If you have a wide boat and you twist it, now the center of buoyancy tries to restore it, doesn't capsize. If you imagine having a boat which is sitting like this, if you twist it, the center of gravity for the weight is above the center of buoyancy and offset, and so it will try and overturn it, just like the Costa Concordia that we looked at. Okay, so that's it. So that's it. So the expressions for this week are the ones that the ones on that first sheet. That's all you need. You don't need those for next week, as you know. I don't know. Say a few things about the test. I don't know if there are questions to answer. I'm happy to answer them. But from this week, these are the fundamental expressions that you need. So these will turn up in a future incarnation of what we deal with in tests. Test. Well, I don't know. I will do this actually and record it for those who... I still get questions as to what is happening for the test, even though we've kind of talked about it. You know, if you're here, that our test, Smiling Billy, review is online. And so you can review that. You have some idea of what it's about. It's in this classroom. It's on Monday and Wednesday and Friday. There are three different sets of questions on those days. You might get here early. They might start things up at 7:55 if you arrive here. The couple of people who are doing this in quiet circumstances, because they're allowed to by the university, we'll get it served to them on Canvas. That will also open at 7:55. It's a 30-minute test. It'll stop at 8:30 or 8:30 something, 8:31. Each question, just like the post-COVID questions from 2020 onwards, is a question with sub-questions which hopefully don't lead on from each other. They're not multiple choice mainly. There might be one or two out of the 6 to 8 that's on a single test, but most of them are calculations to put in a box. You're asked to put those calculations in particular units. You'll have the test and an equation sheet. The equation sheet is the bottom of this video, which you'll get verbatim. The back of it you can use as scratch paper or get scratch paper. I think Matt and Junpeng will come and put the tests out on the desks every other seat. They'll put the test down with the equation sheet on top, so you're welcome to come in and sit down, and they'll probably start you off when they start you off. You're welcome to ask them questions as to if you don't understand something, and they'll answer you if they think they should, I think. Bring a calculator, pencil. They'll provide scratch paper if you need it, but you can also use the equation sheet. We've kind of narrowed down the questions. Yes, it is only parts 1 and 2, weeks 1 and 2. No buoyancy, no forces on structures, with the exception of forces on a horizontal plane are equal to pressure times area. Don't need to know the centroid. We've used that in the first 2 weeks. And you might want to use that a week today. It actually says it in the test. The other questions, Monday, you need to know that for a flexible balloon, the pressure outside is the same as the pressure inside. We don't usually have mass length time questions. We do this year just because we have less material to talk about, so there aren't very many questions about that, but there are questions that you did in your homework. Surface tension, you know how capillaries work, and how surface tension gives you capillary rise. And the third one, manometry and pressure at a point, you know how to do that. I don't know what else to say. What questions do you have? Don't approach it with trepidation, trying to make you able to show us your best stuff. Come in confident, do your thing, get a good score on these first ones to set you up for the rest of the course. This one is a bit more, sometimes it's a bit more difficult to gauge. Historically, I think the last couple of years, students have done really well on the first test. It used to be they didn't do very well, and I was never sure whether it was because, one, it was less easy to predict what you're going to get because we covered a lot of things, or whether people didn't really get quite into the class yet and were thinking that it wasn't as challenging as it is. So it's not. It's a fair test, I think. I think you'll see from the last 5 years, hopefully you think they're fair. They cover the material we talked about in class. There's nothing in the test that we haven't covered in class and is not covered in this 10, 12-minute video to do this. You've taken tests, I'd imagine, for 1.5 decades, so I won't give you any platitudes about how to do them. I try my hardest to not have follow-on questions so that one question doesn't build on another. So if you mess up the first one, you're disadvantaged. You might want to finish, when you finish your test, take a picture of it, front and back. I'm not sure you'll get them back. Junpeng will grade them by hand. So write your name on it, write your student number on it. Bring a real calculator. Don't use your cell phone, no tablets or cell phones or computers. You might want to take a photograph of your script so you have it. The results will be posted probably at noon on Canvas, so you can check the same kind of solutions that you see in your things. Yes?
So for the equation sheet, in the video kind of just goes over everything, so would the equation sheet just be like all the handwritten
Yes.
equations?
It's verbatim. We're not going to play a video for you. It'll be a PDF. I've got a PDF of this whole page, and it will be. I asked Junpeng if he could figure out how to project it on the screen. I'm not sure whether he's going to do that or not. I was going to say something else before, which I can't remember now. Yeah, you might want to take, the results we posted. Oh, so the answers, they're not really multiple choice, they're numerical answers. You're asked to report them in units, as you've seen in the ones that are post-COVID, which is 2020 onwards. So use those units. I imagine that if Junpeng's doing it by hand, that if you get that wrong and do it in kilonewtons instead of newtons, then he might cut you a break. The answers are plus or minus 10%. So that's a fair latitude. We did that because they were exact answers on Canvas in the past, and so we'll keep with that. And yeah, I don't know what else to say. Look on it as an opportunity. You talked about what my demons are versus you. I never used to like making presentations. So I know that the best presentations I make are when I know my stuff dead to rights, and I'm excited that people know what my research is because I'm going to tell them about it. If I'm nervous about it and I think it's crap and I'm not really wanting to talk about it, then that's when I don't like making presentations. So I think that's the same for tests. Prepare for it, come in confident, be sure of your material. The last two questions are kind of copies of other previous tests questions. And they're actually both pre-COVID. And so 2019 and before. That's a lot of tests, but so that perhaps doesn't help you. And and they're not as long. Tests before COVID were much longer. The ones after COVID get you to calculate this, and then this, and then this, rather than saying you need to solve this problem of the force on the gate, and you have to incrementally do this. No gates. So again, to reiterate for some of the questions I've got, 1 and 2 weeks only, no buoyancy, no forces on structures, no dam questions. Dam questions. Great. Don't get wasted on Sunday night. Okay, thanks very much. Good luck.
Thank you.
Yeah. Have a great weekend.